Okay.
Thank you.
Thank you, Ji. Bismillahirrahmanirrahim. Uh, so, okay, so last time we have covered decimation and interpolation, and especially I gave you this example, one of the applications of decimation where you, especially it is used in JPEG 2000. It's called subband coding, where an image is taken and every column of the image is passed through a low pass filter and a high pass filter. And then they throw away every other sample. So they get two half images. And then they take actually the same image and pass every row of the image through a low pass filter. And again, do the same thing, a low pass and a high pass. So in the slide, you see, G.
Sir, sorry for interrupting, but is the class going on Facebook Live as well?
नहीं, Facebook Live पे नहीं है.
Sir, then we'll have to wait for a bit because students do not have Zoom installed at the moment.
Oh, okay. So let's wait
for 10 minutes.
10 minutes. Okay.
Thank you.
5 minutes. 5 minutes.
Okay, sir.
Okay. Wait कर लेते.
सर
जी
सर जितने देर वेट कर रहे हैं उतने देर मैं क्या सर से क्वेश्चन पूछ सर मैंने आपको एक क्वेश्चन सर था शज़ैम के रिलेटेड. तो सर मतलब शज़ैम के एल्गोरिथम जो उसके पीछे बिहाइंड लॉजिक है वो तकरीबन काफ़ी ज़्यादा सिग्नल से मिलते बनी है ना. तो मैं कह रहा था कि आप अगर वो उसका हमें इतना तो वो क्लियरली भी एक्सप्लेन समझ नहीं लग रही ना कि उसके अंदर क्या हुआ. तो अगर आप सर वो हमें एक्सप्लेन कर दें इसी लेक्चर के अंदर. तो
अच्छा, वो कौन से, मैं तुम्हें जवाब तो दिया था उसका कुछ ना
सर. वो था वो सिर्फ थे कि कितनी वो होती हैं कॉपीज बनती हैं.
अच्छा, तो उसकी बात कर रहे थे ना. इंटरपोलेशन में तुम कह रहे थे 8 कॉपीज क्यों नहीं बनती हैं, 7 क्यों बनी है.
बिल्कुल
यही ना. तो आई एक्सप्लेन इट टू यू दैट एक्चुअली द नंबर ऑफ कॉपीज जो हैं वो टोटल 8 होती हैं. 1 ओरिजिनल कॉपी होती है और L-1 जो है वो एक्स्ट्रा कॉपीज होती हैं. And the reason why there are copies is a mathematical reason behind this. And if you remember last time, I told you the reason as well. And the reason was the relationship between the decimation, the interpolated and the normal Fourier transform is, this is x exponential j omega L. The interpolated version is x exponential j omega L. And then I explained that if you have a relationship which says y is equal to x, and you have a relationship y is equal to Lx. Okay, so y is equal to x. If you plot y is equal to x, so at 1 you have value 1. But for example, let's say L is 4. So now, once you put x is equal to 1 by 4, then y will be 1. So you scale your x-axis, or you divide your x-axis by L in interpolation. And if you do that, if you're dividing your x-axis by L, so that'll make, it'll compress the entire spectrum by a factor of L. So 2 pi will be divided by 4, 4 pi will be divided by 4, 6 pi will be divided by 4. So all the copies you have of the spectrum, will be, so 1 copy, 2 copy, 3 copy, 4, up till 4 copies, because first copy is at 2 pi, it is divided by 4. The second copy is equal to 2 into 2 pi, that will be divided by 4. The third copy will be 3 into 2 pi by 4, and fourth copy is 4 into 2 pi by 4. 4 cancel with 4, it will come on 2 pi. So there are going to be 3 extra copies. So these 3 extra copies will actually make the interpolated signal once you insert zeros. So this is why you see all these copies. Okay?
Yes, sir. Thank you.
Let me know when we can start.
Sir, just a little while.
Okay.
सर
जी
सर वो और जो सर जो मैंने दूसरा क्वेश्चन किया तो सर वो एक्सप्लेन आप कर सकते हैं किसी क्लास के अंदर या वैसे नॉर्मली प्राइवेट पे भी शायद?
वो क्या सवाल था
सर? शज़ैम का एल्गोरिथम कैसे वर्क करता है सिग्नल प्रोसेसिंग के रिलेटेड? वो मैं आपको एक पेपर भेजा था जो उन्होंने पब्लिश किया था।
ओके चलो वो फिर हम किसी वक्त ऑफलाइन कर लेंगे. ओके we'll discuss it offline. ये जो अब once I'm writing on the laptop तो इसमें डिले तो नहीं आ रहा?
नो सर.
क्योंकि मैंने असल में I tried this last night on Facebook, तो Facebook में ना बहुत ज़्यादा डिले आ रहा था स्क्रीन पे लिखने में और उस जगह पे पहुंचने में ना.
नो सर अभी लैग नहीं है.
रेडी है?
नहीं मैं कह रही हूँ लैग नहीं है. I'll just
Lag
confirm कि कितने परसेंट लोग अवेलेबल.
ओके
सर
जी
सर जो आपके साथ वीडियोस है ना जो मतलब फेसबुक पे या जो फेसबुक पे हैं जो या गूगल ड्राइव पे हैं या सर उनकी मतलब कि क्वालिटी पता नहीं क्यों 360 पे भी नहीं चलती, वो 240 पे चलती हैं तो काफी ब्लर आ रही होती हैं सर. तो सर वो अगर आप तो सर अगर सर वो मैं अगर आपकी जो लेक्चर देख भी रहा था जो आप ड्रॉ कर रहे थे चीजें सर वो मुझे बिल्कुल भी नजर नहीं आ रही थी कि आप कौन किस जगह पे ड्रॉ कर रहे हैं या वो एक्यूरेट नहीं नजर आ रहा था. तो सर अगर आपके लिए सर पॉसिबल है तो जैसे सर उस्मान क्या करते हैं कि पहले लेक्चर की वीडियो बना के दे देते हैं ताकि वो हम लोग पहले देख लें और फिर उसी का लेक्चर देते हैं ताकि हम लोग जो है ना अगर जितने भी क्वेश्चन हमारे पेंडिंग है
मैंने अभी ये किया हुआ है. व्हाट आई हैव डन इज आई एम रिकॉर्डिंग द स्क्रीन एज वेल. ठीक है.
यस सर.
सो आपको ये मैं ना जो ये पावर पॉइंट की इस पे रिकॉर्डिंग इसकी वीडियो बना के मैं अपलोड कर दूंगा साथ में.
आपके लेक्चर्स तो ऑलरेडी YouTube पे अवेलेबल हैं तो हम वहां से भी देख सकते हैं.
Yeah, but lectures are already available on YouTube, but I will also make sure that you get the video of the slides. क्या करें भाई?
सर मेरे ख्याल में वी कैन स्टार्ट क्योंकि इसकी वीडियो रिकॉर्डिंग तो अवेलेबल है. अदरवाइज इनकी फिर अगली वाली क्लास का ना ओवरलैप होना शुरू हो जाएगा.
Yes. Okay, let us start. Yeah. So Bismillahirrahmanirrahim. So we were discussing what we learned in interpolation and decimation, and this is one of the topic where we use decimation to do subband coding. And as I mentioned earlier, that this technique is also used in JPEG 2000, which is a image compression technique, where an image is taken, like you see here, and this image is then decimated by first passing it through a low pass filter, every column, then again low pass filter, every row, so, and then a high pass filter. So this last time I mentioned that you have a low pass and a high pass. So this part is low, low, this part is low, high, this part is high, low, this part is high, high. And then you take this part of the image and again repeat the same operation. So this part is low, 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 low. And similarly, you can label rest of the images. And if you look at this carefully, the image size is same. So image information, you have all the information, but now the information is spread according to the frequency. And this is where usually a wavelet transform is taken. And wavelet transform, what it does is the Fourier transform and a wavelet transform, there are two different transforms. A wavelet transform keeps the image or the signal in time domain or space domain. So you still see an image, but it is split into different frequencies. Okay, but a Fourier transform takes an image or a signal and it'll just take it from another domain, which is the frequency domain. So these are the two major differences. And so you still see that what are the high frequency components in an image and what are the low frequency contents in the image. So today we want to start the new chapter, and the chapter is about the LTI system. It's still LTI system, and it's the frequency domain analysis of LTI system, and especially systems which are represented by a rational system function or HOC, primarily an IER system. So if we recap, and we have been studying systems for quite some time now, is so we have so this is input, this is output, this is in h of n is the impulse response, and we know the relationship between y, h, and x, and the relationship is of convolution, that y of n you can find by convolving x of n with h of n. And again, we know there are two types of system. One is an FIR system, and the other one is an IAR system. And so we have a transfer function and an exponential j omega is the Fourier transform. And the Fourier transform, because Fourier transform involves an exponential j omega, and because of exponential j omega, it has once you compute this, it's usually a complex function. And if you put different values of omega, you find complex numbers. So that's the reason usually you plot its magnitude and its phase response. So we have been mostly focusing on the magnitude of the Fourier transform. In this chapter, we'll spend some time to understand what role phase plays in shaping the frequency response of a system. What is the role of phase? So magnitude, we understand that once you have a magnitude, and it will basically tailor the frequency content of the signal according to the magnitude of the Fourier transform or the frequency response. But what is the role of the phase? So we need to understand the role of the phase. And from this perspective, we need to see what happens in an FIR system and an IR system. So this chapter is about learning about the phase response. And so this is these are all the things that we have studied till now. That if you input an impulse, what you get at the output is called the impulse response. If you have an exponential j omega and you get an exponential j omega and back, and what is left is the frequency response of the system. And then we have studied about the magnitude and the phase. So usually this is convolution. In time is multiplication in frequency, and then multiplication, you have magnitudes, they multiply, and the phases you add. So magnitudes multiply and phases you add. This we have already studied. And for an IIR system, we have the transfer function as a rational transfer function, which has a numerator and the denominator. So coefficients of x are the coefficients of x here, the previous and the current value of x, they appear in the numerator of the transfer function, and the coefficients of y, okay, in the difference equation, they appear in the denominator of the transfer function. So we know this much. And we also know that once you compute all the roots of the numerator and all the roots of the denominator. So the roots of the numerator are called zeros of the systems, and all the poles of the transfer function are called pole of the system. And we know for a causal system to be stable, the unit circle is very important. That for a causal and a stable system, all the poles must be inside the unit circle. So this we have studied in detail, that for a causal system, all the poles must be inside the unit circle, because the region of convergence is outside the outermost pole. And if the region of outside the outermost pole and the outermost pole is inside the region of convergence, is inside the unit circle, then the unit circle will be in the region of convergence. So for stability and causality, all poles must be inside the unit circle. This again we have already studied, and zeros we don't care. Zeros could be inside, outside. So we are not really worried about zeros of the system. Zeros could be anywhere. But if you want a system and you also want its inverse, in many applications, you also need to have an inverse of a system. For inverse of a system, zeros becomes the poles and poles becomes the zeros. Obviously, it will just take 1 over h of z is hi of z, because once you multiply the two transfer functions together, you want answer to be equal to 1. It means once you are convolving a system with its inverse system, convolving, you should get delta of n, so that it cancels out the effect of a system. So for such a system, and why we need such a system, many applications like your base station is once you transmit something, your signal goes through an environment which we call a channel. So it is responsibility of your mobile to cancel out the effect of the environment. So it has to implement an inverse system. So inverse systems are very important systems. Usually they are there to cancel out the undesirable aspect of a signal passing through something and then getting into your device. May it be a medical, if it's a medical equipment, then the environment, even the body, if you are taking X-rays or MRIs, the body, its motion, these are all undesirable effects. So an inverse system is used to cancel out those effects. So inverse systems are important, where once you take the reciprocal of a system, your zeros becomes poles and poles become zeros. So for an inverse system, you need to design a system where all poles and zeros must be inside the unit circle, so that once you take inverse, then you still get a stable system. So last point says causal and stable. With causal and stable inverse, all poles and zeros should be inside the unit circle. So this is trivial. And for a system, as it says here, that you have h of z, then you have hi of z. I think somebody's mic is on. Please turn your mic off. So you have a system and its inverse, the transfer function should give you an answer which is equal to 1. And so you have h of n and you have hi of n, and you convolve them. So convolution, remember, in time is multiplication in z domain. So convolution changes into multiplication, and delta of n is the z transform is 1. So inverse system is 1 over your system. So the transfer function of the impulse system is the reciprocal of the transfer function of the system. So your zeros will become poles and your poles will become 0. So a system which has all its poles and zeros inside the unit circle is called a minimum phase system. This is an example. As you can see, its pole is at 0.5 and its zero is at 0.9. So once you take the reciprocal of this, the 0.9 appears as 0 and 0.5 appear as pole. So this is a system which is a minimum phase system. So now the most important again aspect of this chapter is that you need to understand that usually these poles and zeros, they exist in complex conjugate pairs. And whenever you plot, and we will see in MATLAB plotting some of the poles and zeros of transfer functions of FIR and IR filter, and because the coefficients of a difference equation, usually they are real coefficients, okay? So if it is a 10th order difference equation, you will find all the coefficients for 10th order difference equation, they are real. So once you try to find out their roots, so roots will not be all real, okay? Usually, in most of the cases, all the roots will be in complex conjugate pair. So a 10th order IR filter will appear as a root having this complex conjugate pair, a complex conjugate pair, a complex conjugate, something like this inside the unit circle. So roots will always be in complex conjugate pair. So it is important to study one complex conjugate pair. Let's say this is a complex conjugate pair, which is at a radius r and angle theta, same radius r but angle minus theta. So these are the two complex conjugate pairs. So this can be represented as r exponential j theta, and this can be represented as r exponential minus j theta. So two complex conjugate pairs. So one is at r exponential j theta and the other one is r exponential minus j theta. So if you write only studying the two of the poles which exist in complex conjugate pair, you can write its transfer function as well. So its transfer function will be h of z is equal to 1 over 1 minus r exponential j theta and z inverse. And the second will be 1 minus r exponential minus j theta z inverse. So you are going to have two poles, the two roots. One root is at r exponential j theta, the other one is r exponential minus j theta. So you can write them together. If you write them together, and then you multiply them together, okay? So multiplying 1 minus r exponential j theta z inverse with 1 minus r exponential minus j theta z inverse. If you multiply these two, so what we are trying to study is what if you have only two poles and they are in complex conjugate pair. So they exist as a complex conjugate pair. Whatever you see on the upper part of the complex Z plane, you see the same thing in the lower part at the same radius and the same angle. So this is a complex conjugate pair. And all the poles of a system and all the zeros of the system will always appear in complex conjugate pairs. So here in this example, and you will also find out the reason that why they are in complex conjugate pair. So if you multiply these two factors together, 1 minus r exponential j theta the inverse and 1 minus r exponential minus j theta the inverse. So 1 multiplied by 1 will be 1. So then minus r exponential j theta the inverse will be multiplied by 1. And then r exponential minus j theta the inverse will be multiplied by 1. So you will get minus r common exponential j theta plus exponential minus j theta and z inverse. And then once you multiply the r exponential j theta and r exponential minus j theta, so you get this. So you can do this multiplication yourself and you will find out that in the denominator, now you will not find any complex number. So r exponential j theta is a complex number which is represented by this pole, or this pole represented as, and you can see that this is a complex number. And this is also a complex number because the complex plane, it has some real value and imaginary value. But we also know once you multiply a complex number with its conjugate, you get a real number. So what is that real number? In this case, it is 2r cosine of theta is 1 and r square is another. So the coefficients, it becomes a second order polynomial, and the coefficients of the second order polynomial will be a real coefficient. So a real coefficients, we also know that real coefficient results into complex conjugate pair. आपको याद होगा the discriminant minus b plus minus underscore b square minus 4ac divided by 2a. This is the formula we used in our FSC class to find the roots of a quadratic equation. So if the quadratic equation has real coefficient a, b, and c, its roots may come as complex conjugate pair. When the discriminant, which is b square minus 4ac, is a negative number, and once you take it under the root of a negative number, you get a complex number. The complex number appear as a plus and a minus. So, so it is important to understand, number one, for stability, all the poles, they got to be inside the unit circle. So for a stable system, both the poles will be inside the unit circle, means your r will be less than 1. R will be less than 1. And for an unstable system, your r will be greater than 1. So in a second order difference equation or a second order transfer function, by just looking this r square z minus 2, the coefficient of z minus 2 will tell you whether the system is stable or not. If this r is less than 1, so the r square will also be less than 1. So if r square is less than 1, you can comfortably say that it is a stable system. You don't need to even worry about plotting the poles of the system by just looking at a difference equation. And remember, z minus 2 is the coefficient of y n minus 2, and making sure that coefficient of y is 1, then you can directly comment whether your system is stable or not.
लेकिन हिस्ट्री वाले ने अभी साइन नहीं करवाया सेक्रेटरी से.
So
भी मैंने कॉल किया, वो ये
मारिया, आपकी आवाज आ रही है बीच में. Okay, so here, so by just looking at the difference equation, we can comment whether the system is stable or not. For example, if I write a difference equation, y so if I write a difference equation as y of n minus 6 y of n minus 1 plus 0.8 y of n minus 2 is equal to x of n, for example. So just by looking at the coefficient of y n minus 2, I can comment whether system is stable or not. Okay, I need not even plot because I know this is R square of the transfer function. I know that it is this R square. So if R square, what I'm saying, G, how do we know that if you write a second order difference equation, just look at the coefficient of yn minus 2. If the coefficient of yn minus 2 is less than 1, okay,
Yes,
because it is R square. If R square is less than 1, then R will also be less than 1. Okay.
Okay, sir.
So if R is less than 1, it means that this conjugate pair. So our second order difference equation represents a system which has two poles and they are complex conjugate. They are in complex conjugate pair. So looking at this equation, yn minus 6 y of n minus 1 plus 0.8 y of n minus 2, I know once I take its transfer function. Okay, so this 6 represent 2r cosine of theta, and this 0.8 represent r square. So just by looking at the second order difference equation, I can calculate the value of r, which is the radius, and I can also calculate the value of angle theta. By just looking at this, I know 2r cosine of theta is equal to 6. If I know r, then I can find out the value of theta as well. So I can plot the poles of second order difference equation by remembering that a second order difference equation is actually 1 minus 2r cosine of theta z inverse plus r square g minus 2. So knowing this, at least it can give me comfort that whether my system is stable or not. And as perhaps I mentioned once in a class, that one of my master student actually kept expanding this from second order to third order to fourth order. And just by looking at the coefficients like we are doing now, he could able to say whether the system is stable or not. So he went to, quite higher degrees of the polynomial, and still he would able to see whether all the coefficients will come inside the unit circle or not by just looking at. And remember, and you can perhaps by doing it, you can do it yourself. Those who are good in mathematics, they can just start. If you have 3 poles and real coefficients, the 2 poles will come as a complex conjugate pair and one has to be on the real axis. Okay, if you have 3 poles, 2 will be in complex conjugate pair. So 3 will always appear like this. 2 as a complex conjugate pair, third got to be on the units, on the real axis. It has to be real. Otherwise, coefficients will become complex. So if you have 4, so 2, 2, they will be in 2, 2 pairs, 2 pairs and 2 pairs. If you have again 7, so you will have all the 6 in complex conjugate pair, and the 7th one will be on the real axis. So if you have odd number of pairs, and we'll see shortly in MATLAB, by forcing the system to have even or odd number of coefficients, and you will find out that this relationship is true, that any filter design technique would ensure that all the coefficients of your difference equation, they are real coefficients, because a complex multiplication would first make the signal complex, and then secondly, that requires like 4 multiplications and 3 additions, real, imaginary, real, imaginary. So you don't want to get into a complexity, because it then increases the complexity of the system by a factor of 4, and which you don't want to do. So this is a very important aspect, and we are going to see this in MATLAB shortly. The second important aspect is the phase, which we have not been just ignoring, that let's not worry about the phase, let's only focus on the magnitude of the frequency response, because magnitude is important. It tells you how it is going to tailor the shape of the frequency response of the signal, what frequency it will eat up, what frequency it will amplify, what frequency the system will let go. But here, what the phase does is, so to understand the implication of a phase, a term which is called a group delay, as the slide reads, the group delay is used. A group delay is the negative derivative of the phase response. So its definition is simple, that whatever phase you have, so you take negative derivative of the phase, it gives you another function, which usually either it is a constant or a function of omega, and this function of omega is called phase or the group delay of the system. So group delay is an important property of a system. Usually once we are designing a system, we want to see, and shortly I'll show you, we want to see, number one, the magnitude of the frequency response, because that is very important for you to see. Then you want to see, if it is a IER system, you want to see whether all the poles are inside the circle. So that's the second thing you want to see. And the third thing you want to see is the group delay. So you want to plot the group delay, because it's such an important aspect. So it's important that we understand, comprehend this. So it says the deviation of the group delay away from constant indicates the degree of non-linearity of the phase, thus giving a measure of phase distortion. And shortly we will understand what the statement is saying, that ideally group delay should be a constant. So now let's try to understand. If you remember, we discussed this, that once we were discussing Fourier transform, that Fourier transform of an even function, a real and even function, is real and even. Okay, so if you have a signal like this, -1, 0, and 1. It is 2, it is 4, it is 2, for example. This is a real and even signal in time domain, so this is x of n. So if you have a real and even, very, very important, a real and even signal in time, you will get a real and even function in frequency. There you won't see any j in it. You won't see any exponential j in it. So let's take its Fourier transform to figure this out. And again, this is an important concept, and make sure that you understand it. So the Fourier transform, and we all should able to write the Fourier transform by just looking at the signal. The Fourier transform is 2 exponential j omega plus 4 plus 2 exponential minus j omega. So we know, right, from our from chapter number 2, we know that we can easily write the Fourier transform or DTFT of a signal, of a finite duration signal drawn in time domain. And all we have to do is just whatever is written in the numerator on the scale. So this becomes exponential of minus j omega. So this is the signal. And you will always able to pair these two up, always. Whenever you have a value on the negative side and a value on the positive, they are the same values. You will always able to combine them into a cosine function without a j in it. So once you combine, we know that exponential of j omega plus exponential of minus j omega is 2 cosine of omega. So this will become 4 plus 4 cosine of omega, because exponential j omega plus exponential minus j omega divided by 2 is a cosine. So exponential j omega plus exponential minus j omega is 2 cosine. So 2 is already there. So 2 will make 4. So as you see now, the Fourier transform, even if you plot it, it is a cosine, a raised cosine. 4 se raised हुई है, it's a raised cosine, and cosine is an even function. We know what a cosine is. Cosine is an even function of omega or theta, whatever. So the Fourier transform of a real and even, also we call it a symmetrical signal. This is a symmetry. So it has a symmetry. What you see on right hand side is the same on the left hand side. Even function definition is if you replace n by minus n, you get the same. If you flip this, you are going to see the same signal in frequency domain and as well as in time domain. As now this is our, if this is h of n, then this is our frequency response. So in frequency response, you don't see any J. It's all real. If a function is all real, so once you take its magnitude and its phase, so this whole thing will be also the magnitude, because there is no J in it. Like you have a number, let's say number 5, and I ask you what is the magnitude and phase, you say magnitude is 5 and phase is 0 because there is no J in it. In order to find the phase of a complex number, you need to take tangent inverse imaginary over real. So tangent inverse imaginary is 0, and the real imaginary over, so imaginary is 0 and divided by 5 is 0. So tangent inverse of 0 is 0. So there is no phase in it. So we call these systems as zero phase system. So zero phase is an important terminology. A zero. Why they are zero phase? If an impulse response is real and even, then your frequency response is real and even, and there will be no phase in it. Okay. So once there is no phase in it, we call this zero phase system. But there is one problem in zero phase system, and the problem is whenever you have something on the negative side in the impulse response, it means it is not a causal system. It will require a future value. Okay. If you remember that, it will require a future input value. This -1, once you put it in the convolution, it will require xn plus 1 in the convolution. So you say, oh, I don't want to design anything which is non-causal. I don't want any value of my impulse response to appear on the negative side. So what should we do? We should shift it in time to make this causal. So the best technique to design an FIR system is that first you design something which is real and even, so that it has a real and even frequency response. And in the second step, what you do is you shift it to make it non-causal. But a shift in time is multiplication by an exponential. So once you shift this thing in time, what will happen that you are going to have? So if you do that, if you shift this in time, so you are going to see your function will appear as this. Okay. So the same signal will now start from 0, 0, 1, 2, 2, 4, 2. Okay, so simple that you have something which was centered at 0 and symmetric. You design it so that the frequency response is real and pure, and then you shift it in time. Once you shift it in time, it is no more symmetric full signal, but its frequency response, which was real and even, which was 4 plus 4 cosine of omega, will now be multiplied by exponential minus j omega, the amount of shift. So a shift in time is multiplication by exponential minus j omega. So again, this is very important concept to understand, that you design something which is real and even in time. And I'll show you in MATLAB that whenever you design in MATLAB any FIR system, it'll be a symmetrical. You'll find a Fourier transform which will be a symmetrical function of n, and then you will find that it is shifted in time. And once you shift it in time, now you have a term where this is all real and this is the, so it is in classical R exponential j theta form, where you find the magnitude as a even function of frequency, and then you find the phase appearing as the amount of shift. So theta, if you compare theta with exponential minus j omega, j exponential. So theta, which is the phase, is equal to minus omega. This is the phase of the frequency response. And now if you take its derivative with respect to omega, and that too minus derivative, okay? So derivative minus derivative with respect to omega. So minus minus is 1, you get 1. You get 1. So it is equal to 1. So whenever your phase is something like this, minus alpha omega. So for FIR system, you are always going to see a phase which is minus alpha omega. And with why? Because it is exponential minus alpha omega. Alpha is the amount of shift you make to make your symmetrical impulse response a causal system. And so group delay will be a constant, will be equal to alpha, which is a constant. So you always want your phase or your group delay to be a constant, because it represents that you have zero phase. So your frequency response is not going to distort the phase. And shortly we will understand it more. It is not going to distort the phase of the different frequency contents in your signal. It is only going to delay them by an amount alpha. So this is the important aspect. So always your x of n should be real and even, so that you have exponential j omega real and even. Then you delay it by a factor of nd or alpha, so you get this real and even, and this appears as an exponential minus j omega nd. Nd is the delay. So this is the classical form where this is r, this is exponential j and theta. So theta is minus omega nd, minus omega nd. Now you take the negative derivative of this, you get it. So nd is the group delay. So group delay is a constant. It is a derivative of your phase response. Derivative of your phase response is this. So why this is important? Because we know that y capital exponential j omega is equal to h exponential j omega multiply by x exponential j omega. The magnitudes they multiply, phases you add. So we have already seen this relationship, which is an important relationship in understanding that what phase is going to do, how the phase is going to harm the phase of your input signal. Here it says that the frequencies, this is the relationship, convolution in time is multiplication in frequency. So the magnitude, they multiply, and phases, I don't know why it is getting crazy if it gets to the lower part of the laptop, but the phases you add, it means the phase of h at different frequencies will be added into the phases of the different frequencies of your input signal. So this is called the phase distortion. We want this angle of h to be 0, so that I don't want different phases of my frequency to be altered or changed. And now we are finding out that you cannot keep it 0, because 0 phase can only happen if a system is non-causal. So in order to make it causal, there will be a linear phase added, but linear phase translates into simple delay. That phases will not be distorted. Our signal will, the entire output signal will be delayed by a factor nd. So group delay is the negative derivative of the phase response, and this negative derivative of the phase response should ideally be a constant. Okay, should ideally be a constant, so that once you split your frequency response into two parts, there should only be a magnitude term and an exponential of minus j omega nd term, so that you don't have a complex phase. And shortly we will see when do we get a phase term which is not linear, like which is not like exponential minus omega nd. When do we see that? And shortly we are going to see it. So, so we understand that the ideal, even the ideal filter, which is a sink. Remember, the ideal filter is a sink. The inverse. This is an ideal filter, omega c minus omega. This is an ideal filter. If you take its inverse Fourier transform, it is sine omega c n divided by pi n. If you plot this, this is a symmetry. This is a symmetric signal, and if you take plot samples and time domain, you will find a perfectly symmetric thing. And just we discussed that you don't want to see any value on the negative side of the time axis. So you got to cut it to make it finite, and then you have to shift it. And that shift, once you shift it, and then you take its inverse. So shift in time means now it is no more one, rather it is the amount of shift that you are causing your sink to shift. So once you shift your sink by nd, the one will change into exponential minus j omega nd. This is the phase term, and it has a phase which is called a linear phase and a group delay which is going to be a constant number. So so this is what in reality, whenever you design a filter, it will look like a sink FIR filter, and then so it will have a linear phase, and once you shift it, okay, so a phase term will appear, which is a linear phase term, and its group delay will be a constant, which is equal to nd. This is what I can do is let me show you in MATLAB so that you understand. So in MATLAB, so here is MATLAB. So MATLAB has these are the apps, and so here is the filter design. This is the filter design application. Very, very powerful tool in MATLAB that you can actually use to design different type of filters. So I hope everybody can see this filter design screen. And let me just use a default. So default is it is trying to generate a filter, which is an FIR filter. Okay, and these are the specifications. It's the sampling frequencies 48 kilohertz. If you want the frequency still 9.6 kilohertz to pass, and 12 kilohertz, and after this you want them to stop, and you stop them by 80 dB down. So 80 dB down means 10 to the power minus 4. So you want the unwanted frequencies to be killed by a factor of 10 minus 4, which is 10000. So you want them to be divided by 10,000. So once you say design, it will design a filter for you. So 0 dB means 1. So here the scale is dB. 0 means 1. So it let these frequencies to pass. And minus 80 dB means 10,000, 1 over 10,000. So it'll kill all the unwanted frequencies by a factor of 10,000. So in here you see different things. So first, let's see the impulse response, because you want to see the impulse response. So impulse response from 0 to whatever value, you always see that it is going to be a symmetric function. It is going to be a sink-like function, and always symmetric. A coefficient you find here, will you find another similar coefficient here, coefficient here, coefficient here. So it'll tell you the symmetry of the function. So number of coefficients are 50. So you always want to plot this, because you take this, and this is your h of n. So you convolve your signal with this, and in doing that, you will find that this system will eat up all the unwanted frequencies from your signal, which are beyond 9.6 kilohertz. Then the second thing you want to see is your poles and zeros. So you will not find any pole in the complex plane. You will find only zeros. And as you can see that all zeros will appear in complex conjugate pair. If there is any zero which appear, there may be like 2 zeros, they are appearing on the real axis, but every zero complex conjugate pair, complex conjugate pair, complex conjugate pair, complex conjugate pair. So whether they are poles or zeros, they will always appear as complex conjugate pair. This is the second thing which you need to remember. The third thing you need to remember is your group delay, which is negative derivative of the phase. It is always going to be a constant for an FIR filter. As you see, it is 25. So 25 is the amount of delay. So you have a system which is symmetrical. Total number of coefficients are 51, and then you shift it by 25 to make it causal. So the shift will appear as a group delay, which is a constant. So we love to have a group delay which is constant, because this tells us that my system is not going to hurt it's not going to damage different frequency content, the phases of different frequency contents in the signal. Okay, it is only going to delay. It will eat up all the frequencies which I don't want, and then it is going to shift rest of the frequencies in time. So we love to have a system like this. Okay, so this is something which we want to see, that it should be like this. Okay, so now let's go back to so now we have seen that once you design a filter, FIR filter, or any type of a filter, you must go and look into the frequency response and look it into the group delay and see that whether it is a constant or not. And so this is the filter we just saw, and we saw its impulse response, and we saw its group delay. Okay, good. So now let us design an IAR filter. Okay, same tool, designing an IAR filter. And let me explain to you. I'll get back to this. Maybe here. Okay, let me see. The simplest IAR filter has a transfer function which is 1 over 1 minus A Z inverse. This is the simplest IIR filter you can design, which has only one pole. Even you let this pole to be real, okay, I mean on real axis. So its transfer function will be, its frequency response will be 1 over 1 minus A exponential minus A omega. Now you compute its phase and compute its magnitude. Given this, it is not very trivial. It's not very trivial to find out the magnitude of this frequency response and the phase of this frequency response. Why? Because now there is this ugly exponential minus j omega, which is appearing in the denominator. So it is not very trivial. If I give you this, it'll take you some time to find out the phase. And if I ask you even to plot the phase, so it's not going to be that straightforward, because in order to find out that, you need to convert this, the j, if you remember from your high school algebra, you need to bring this j from the denominator to numerator. Only then you can say this is real plus j imaginary. And for doing that, you need to multiply this with its complex conjugate. Divide, multiply, and divide with its complex conjugate. So it's going to take some mathematics for you to find out. So you multiply it with its complex conjugate. So in the denominator, now you will have something which is all real, because once you multiply a complex function with its conjugate, you get real, and we have seen it 1 minus 2r cosine of omega plus r square z inverse. So you are going to see the same thing in the denominator here, which will be 1 minus 2a cosine of omega exponential minus j omega plus a square exponential minus 2j omega. So it is okay in the denominator. Now in the numerator, you have an exponential j omega. You need to split it into two parts, cosine of omega plus j sine of omega. Then you have a cosine part here and a j sine part here. Then you take tangent inverse and it will become something which looks ugly. If you plot, it will look ugly. So the issue with the IIR filters are that once you are going to design, okay, once you are going to design, let's design the same filter using the MATLAB toolbox. So we have here, the MATLAB toolbox is here, okay. So in MATLAB toolbox, now I am going to design the same filter. Here is the MATLAB toolbox, sorry. Okay. So now I ask MATLAB to use IIR specs. I'm not changing the specs of the system. The specs are the same. And I asked me to design this for me. Very nice filter. It has designed, sorry, I want this to be 80 dB down. 80 dB down. Okay, so 80 dB down and IR filter. So this is 80 dB down, 0 dB. So very nice filter. We have seen it in for an FIR case where it had coefficients 50, but for IR it's only an 8th order filter. So IR filters are usually computationally more. They are less intensive, so more feasible to implement. The issue with them is that once you look at their group delay, it is going to be nonlinear group delay, okay? Because there will be that ugly function of omega, which is tangent inverse imaginary over real. And then you further take once its derivative, it'll take you quite some effort to actually compute the derivative of something which is tangent inverse of something which is a function of omega. So it's not going to be that simple. On the other hand, in case of an FIR filter, it was a very simple affair. You design something which is all real, then you shift it so your phase appears in the classical R exponential j theta form. You need not to take any tangent inverse because your magnitude is just as is, and then your phase is something which is linear. You take the negative derivative, you get a constant number. Here, the group delay appears like this. And the unit of group delay is number of samples. This is how much your frequencies are going to be delayed. That is why it is called group delay. And 25 means all the frequencies are going to be delayed by 25, or the signal is going to be delayed by 25. But in this case, if you look at this group delay, it is changing from 0 going to 10 to 20 to 40 to 50. Like there will be some frequencies, they will be delayed by 50 samples. Then there are going to be some frequencies which will be delayed by 40. Then there are few which will be delayed by 30, 20, 10. And there will definitely be few frequencies which will be delayed very little. But the important aspect is that all the frequencies in the signal, because signal is nothing, remember, but combination of many frequencies, and they are going to be delayed differently. It means your shape, the IR filter will distort the shape of the signal. Shortly, we will understand this. But remember that whenever you are designing a filter, you must go and look into the phase, the group delay plot. So see how the group delay look like. And then for IR system, there is no point in looking at the impulse response, because we know impulse response will be an exponentially decaying function of time. It will not be symmetrical like a sink in case of an FIR filter. So you see an exponentially decaying, and inside that exponential there will be a cosine running. Inside it is not symmetric, and because it's not symmetric, that's why it does not have a constant group delay. So, but more important, you want to see the poles and zeros part. So you see all the poles. Two things I have told you. One is that you are going to see all the poles appearing in complex conjugate pair. Okay, this is first thing I told you. And second thing is that they all will be inside the unit circle. I told you the importance of the unit circle, that whenever you see this in MATLAB will plot all these signals, your poles, and it is going to plot a unit circle just to show you, to give you comfort that all the poles are inside the unit circle. Though there is one pole which is very, very close to the unit circle. You need to make sure that once you quantize, because here MATLAB has designed this filter using double precision arithmetic. And perhaps we'll talk about this in this course, or once you learn the next course, which is digital system design, you learn more about the quantization and what quantization does to the location of poles. But all the poles must be in the unit circle. On the other hand, if you force the number of coefficients to be 11, okay, now you're forcing the filter to have 11 coefficient. Let me see it. So now you will find out what I told you earlier, that all the poles are inside the unit circle, and there is complex conjugate pair, but one pole will be left alone because there are 11 poles, and that will always be on real axis. So that once you look at the A's and B's, this is the B's and A's. Once you look B's and A's, they all appear as real numbers. So this is important that you, but again, once you go look at the group delay, you will not be happy, because you will see a group delay which is not a straight line, and you say, wow, should I still go ahead and use the IER filter? Am I concerned about the phase? And shortly I will tell you what is meant by the phase. The phase distortion. Should I let this phase distortion happen? Or in case of an image, I'm going to shift some of my pixels from one part of the image to another part. And if it is my signal, it is going to shift some of the frequency contents differently. Okay. So it's again your decision depending upon the application, whether you can absorb. But remember that it gives you a computationally efficient realization of the same filter, which has almost the same magnitude of the frequency response. It will eat up. Okay, it will kill all the frequency happening beyond this around 9 point something, 9 point whatever, this is 9.6 kilohertz. So it's going to kill all those frequencies, but going to cause phase distortion. So phase distortion. What is phase distortion? Very simple to understand. The phase distortion. Look. Okay, so here I have designed all these filters. So phase distortion is like if you have a signal, it has different frequency. Let's say it has this frequency, this frequency, this frequency, this frequency. And they are not just jumbled up together. You see them separately. You see a low frequency, a very low frequency, a medium frequency, a high frequency, a very high frequency, low frequency happening at different locations of your signal. Okay, like your ECG. If you look at your ECG, it is something like this. Okay, so different frequencies happening in different locations of the signal. Pass it through an IR filter, which has an ugly looking group delay response, then this response is telling you, I'm not going to hurt this badly, so I will not change their location. So they exist where they exist. I let them pass and not change their location. But like medium frequencies, I am going to shift them by 20 samples. So once this signal comes out, somewhere else, it will appear after 20 samples. And even higher frequencies will appear 40 samples away. And higher frequencies will appear at 50 samples away. So the same signal, what you see here, will be distorted. And if you have higher frequency in the start, if you have a signal where you have higher frequency in the start, then you have lower frequencies, they are going to change. This is a good example. Here, a signal is created where you have a high frequency component and a low frequency component and a medium frequency component. So there are three different frequencies. You start a signal, you generate a frequency, then you finish that frequency in order to comprehend the effect of group delay. Then you generate another frequency and then you finish that off. Then you generate another frequency. Or this is mostly the case in, as I mentioned, in EEGs and ECG signals where you see all of this. And so once you look at the Fourier transform of the signal, obviously you are going to see three frequencies: a low frequency, a medium frequency, and a high frequency. You see three frequencies: a low frequency, a medium frequency, and a high frequency. And then you are going to see a replica of that, because we know if a signal is real, the Fourier transform is symmetric. So you see the symmetry. So you find the three frequencies and then image appearing from 0 to 2 pi. You're going to see a replica of that. Okay, that is fine. Now, for some reason, you want to filter out the high frequency. You say, this is noise. I don't want this frequency to be there because it is just a high frequency noise appearing somewhere, coming from somewhere, but not really hurting my frequencies because it's appearing, like this. But I want to filter this out. So you say, design a filter. We should eat up the high frequency, but let the medium and the low frequency to pass. So you want to pass this, and you want to filter out this. Obviously, you are going to design something like this, a filter in frequency domain, which look like this. So you go in MATLAB and without, because you don't know about group delays, so you are not careful, and you say, why not to design a filter which is efficient? So you design an IR filter. An IR filter looks like, as I showed you earlier, looks like this. This is my IR. Okay. IR filter is like this, and you say, okay, this is minus like 80 dB. So it is definitely going to eat up. It is shown in dB, so you see, a little bit elevated stop band, but actually it is minus high. It's minus 80 dB, like that. So it definitely is going to eat up the high frequency. High frequency will not appear. But the issue is with the rest of the two frequencies. If you look at this frequency, which is the low frequency, it is going to be delayed by around 200 something, 220 or something samples. So this will appear, a group delay means this frequency will now be shifted to a new value, which is 220. And this frequency, which is the medium frequency, will be delayed by something around 40. So looking at the group delay, you find out different frequencies in your signal, go up and see how many samples will each be delayed. You are less worried about the frequency which this is going to eat up. So if I go back to my signal, I find out that this I don't care because this will be eaten up. But my low frequency will be delayed by 220 samples. So it will go in the output, appear after 220 samples, and my medium frequency will appear at 50 sample delay. So what will happen? Your low frequency will appear after your medium frequency. It will distort the shape of the signal, and you say, oh my God, I don't want to see my signal like this, because the relative location of different frequencies are important for my application. So once you pass this signal through this filter, it will eat up this. So you don't worry about that. But it is going to delay this frequency about 220 samples, and this 50, so they will change their location in the output. You get what you want, which is the undesired frequency will go away, but you don't want your signal to look like this. Okay, so this is the price you pay for implementing an IIR system, that it has a phase distortion, and phase distortion is a measure of how much your group delay deviates from a constant value. If it is a constant value in the band which you care, because those are the frequency which are going to be left in the signal, then you are not worried. What will happen if you pass the same signal through an FIR filter? It will eat up the unwanted frequencies. It will not distort the shape of your signal. You will still see the same signal appearing at your low frequency first and your medium frequency after that. So, and again, it depends. Sometimes they may jumbled up together, both of them, because let's say if it is not delayed by 50, rather it is delayed by 180, and the other one is by 200. And then again, you will be surprised to look at your signal and you say, wow, this is not what I input to my system, and the system has, though taken out the unwanted frequency, but it has totally changed the shape of the signal, which perhaps I don't like. So you go back and try designing a filter, even if it's an IER, which should deviate a little from a constant value in the pass band. I don't care about the stop band, because those frequencies are not going to be there. So I want to ask if you have any questions till now, please do ask. And कोई सवाल हो आप में से किसी का तो आप पूछ सकते हैं मुझसे.
No, sir.
No questions. Okay. अभी डॉक्टर अली, हमारी क्लास कब तक है?
25 पे इनकी अगली क्लास है.
25 पे अगली क्लास है. तो हमें अभी मतलब हमने वैसे तो शुरू थोड़ा लेट किया था, लेकिन ठीक है, मेरा ख्याल है कि दिस इज बिकॉज ये थोड़े से इस तरह के कॉन्सेप्ट्स हैं, आप इनको देखिए. और व्हाट आई डू इज आई हैव आल्सो रिकॉर्डेड द प्रेजेंटेशन, सो आई विल ट्राई कि ये जो आपकी हमारी ये रिकॉर्डिंग है इसकी प्रेजेंटेशन की भी, वो भी मैं आपको अपलोड कर दूँ कहीं पे. तो ठीक है, थैंक यू वेरी मच. तो